Now you will just find out that when we get to this point, we have performed the lateral selection, that is using the thresholding or the selection weight. And then so now we are going to go to the second part, that is about the selection for crossover. For the selection for crossover, that means assume that we have the n-kipped population, that is 4. So we are going to select them to some of them to act as the parents. Once we find that we have those parents, and then we can perform the crossover according to this method. So these methods, I just mentioned a few of them, and then if you're going to look into literature, we will find out that we have more than that. Now for the swapping, we have single point crossover, double point crossover, uniform crossover. We have done that before. So in continuous genetic algorithm, we are going to do the swapping using the real valued function instead of the binary string, but the idea is more or less the same. For the banding and extrapolation, that means for these two methods, for each one of them, so we have two ways to do the banding or the extrapolation, and then I'm going to explain that to you later on. And now single point crossover, quickly I'm going to explain or to recall what we're going to do. For example, when we have parents 1, parent 2 selected by whatever selection method we use, so we are going to have 2 parents to generate 2 offspring for crossover after by crossover. So now PM1, PM2, that is the parent 1, PD1, PD2, so and so, that is for parent 2. For example, we can just simply pick, say, this is parent 1, this is parent 2, so we will have this chromosome and this chromosome. So we call this is just PM1, this is PM2, this is PD1, this is PD2, so and so. Okay, now just the same thing that we are going to pick a crossover point. For example, this is the crossover point, and so we just simply swapped these chromosomes after the crossover point. So the blue goes up, the green goes down. Yeah, just simply do the swapping. And double point, we choose 2 crossover points randomly. So we just simply swap the thing in between. Yeah. Now uniform crossover, that is, say we are going to go through each one of them. Say if we are going to choose a random number in the range of 0 to 1, if it is less than the probability of crossover, we are going to swap. Yeah, we're going to swap. Otherwise, we do not swap. So that is exactly what we have done in the binary string in the binary genetic algorithm. So again, the disadvantage of this kind of crossover, that is, we only exchange information. That means no matter how many bits or no matter we are going to swap each gene or each real value, and then so we cannot generate some new information. Yeah. So say we have n var variable. That means if we are going to do uniform crossover, so that means either swap or not. So the total number of combination for the uniform crossover, that is 2 to the power n var. Yeah. So that is the total number of combination for the offspring. We cannot generate anything more than these combinations. But the advantage of using swapping, that is very simple. We do not need to do any calculation, just generate crossover point, swap. And now we are going to talk about another method, that is banding. Banding, that means we are going to use these 2 equations. Yeah. Why we name that as banding? It is because we are doing the linear interpolation. Say we're going to have parent 1 and parent 2 choosing, we choose these 2 parents from the n kept. So we are going to have these numbers, and then say we are going to pick some number. For example, these 2. If we are going to do banding, it means that we will do beta times PM1. If this value, that is 0.2, and then this value will become 0.2 plus 1 minus beta times BD1. If this number, that is minus 0.5, and then this one will become minus 0.5 beta, that is a value. When we can pick a constant value, or each time we are going to randomly generate that. But anyway, it is in the range of 0 to 1. So that means if we are going to use this equation, no matter what we are going to do, we will generate any number in between these two ranges. That would be these two numbers will serve as the bound, the upper bound and the lower bound of this range. Yeah. So then, for example, this is 0.5 minus 0.5, and then this is 0.2 PD1 PM1 in the range. In this range, we will just randomly pick some number according to this equation, if we are going to choose a random number for beta. Yeah. Okay. So that means the disadvantage is that when we look at PM1 and PD1 according to this equation, that means no matter what we are going to do, we can only generate the number in this range. We cannot generate any number outside this range. Yeah. For example, if this is the x, that is the first decision variable, that is x, in the range of minus 10 to 10. So we have a large range right here outside minus 0.5 to 0.2. That could be some potential good value for this problem. But now this range is bounded by PM1 and PD1. Yeah. Okay. So this is the new value generated by PMN and PDN. And P new 2, that is, we do exactly the same thing. If this is the crossover point, we are going to use PM1, PD1 as well. But now the beta position is different. The first bit, that is 1 minus beta. The next one, that is beta. Yeah. As I mentioned before, that we have two methods. I'm going to give you some ideas about what they are. Now, method 1, that is bending at the nth point. This is the crossover point. Crossover point randomly generate 1. For example, we are going to pick this is the crossover point. Yeah. So we are going to compute PD1 according to these two equations. So PD1 will go to this position, PD2 will go to this position. And then after this point, note that this is PD, this is PM. So we just simply swap. That means after certain point, the PD from the offspring 2 will go to the upper part, and then the PM from the parent 1 go to the lower part. Yeah. So this is just do the swap. This is the method 1, and then so we are going to do the method 2. Method 2, that is, after we choose this crossover point, every element right here, we are going to compute the PD1 and PD2 according to these two equations. Yeah. So this is the PD1, PD2 using the PMN and PD and to calculate PD1 and PD2. Now this one we are going to use PMN plus 1 and PDN plus 1 to calculate this PD1 and PD2 and so on. Yeah. So this is the method 2. And now I'm going to talk about the extrapolation. Remember that in banding, as I mentioned before, we cannot generate anything outside the range bounded by PMN and PDN. That is, this issue I mentioned, anything that is we can only generate within this boundary. Yeah. So what about this value? So in order to overcome this limitation, and then so this is what we are going to do is the extrapolation. Now the extrapolation, the equation that is becomes something like that. That means we have PMN and PDN, that is from parent 1 and parent 2. For example, we are going to choose the crossover point right here, and then this will be the PMN, this one will be the PDN when n equals 4. Okay, now instead of bounding beta within 0 to 1, now beta that is greater than or equal to 0. If you are going to choose beta equal to 0, and that we do not introduce any new information, but anyway, beta that is a random number which is greater than 0, we do not apply any limit to that. So that means it could be any value larger than 0. In that case, the potential solution is that the p new value will be out of the range of this decision variable. Yeah. So for example, when this is 10,000, it may be very large, and then so there will be a chance that it is out of the range. In that case, if those element is outside the allowed range, and then so we are going to discard it, and we generate the number of beta so that the PD1 and PD2, they are within the range of the decision variable at that particular position. Yeah. So again, we still have these two methods. The method 1, that is choose a crossover point. At this particular crossover point, that is n in the nth position, and then we compute p new 1, p new 2 according to the extrapolation equation. After that, we are going to swap those genes. Yeah. And then method 2, that is when we pick the crossover point, after the crossover point, every element right here that is computed by the extrapolation equation. This is an example. For example, we choose chromosome 2 right here in the n-capped chromosome 2 and chromosome 3 as the parents. So this is parent 1, parent 2, and then so I just put it right here, and then now beta, that is 0.0272. Now this equation, assume that this is the crossover point that is at the first position. So we are going to apply this equation. So you will just find out that this is PM1, this is PM2, this is PD1, this is PM2, PD1. This equation, that is PM1 minus beta times PM1 minus PD1. So that's why we have 0.18 here minus 2.6 right here. So this is the PD1. And then now we are going to swap this two number, that is the method 1. So we come up with 6.2, 8.9 in the second position. So we do the same for the next element. This is p new 2, using exactly the same information right here. In the next slide, after we do the crossover, and then so we are going to do mutation. The mutation, and then so we use the same concept. That is, we need to choose the mutation weight. That means we have a lump in the population. Now, if n pop, that is 8, and then so we will have in total 8 chromosomes right here. Yeah. Now remember that this is the n cube. The cost is in ascending order when we do minimization, and then the last 4 actually coming from the crossover. After we do the crossover, we replace the bottom half. So right here, we do not do the cost. We do not evaluate the cost. Yeah. So we choose the mutation weight in the range of 0 to 1. And then now the total number of variables, we are going to pick them for mutation. That is mu times n pop, that is 8, minus 1, because the first one we are not going to perform mutation if elitism is implemented. If we are not going to implement elitism, and then we will not have this one. Yeah, ny, that is the number of decision variable in each chromosome. So this is the mutation equation. Now Pn, that is corresponding to each chromosome, we have the parameter 1, parameter 2, and then one of them parameter n, and then the last one, that is parameter n raw. And then that means we are going to perform mutation for the selected chromosome. For example, if we are going to select this one, and then this one will be the value of Pn plus sigma, that is a constant. We choose a constant that could be anything. And then now n01, that is the standard normal distribution. It means that we are going to generate a random number using the mean, that is 0, and the standard deviation, that is 1. In that case, it doesn't mean that this random number generator will generate anything in between 0 to 1. Actually, we are going to generate any number according to this distribution. That means it is possible that we will have a very large number generated, but the chance is very small. Yeah, the chance is very small. So what happens if we are going to generate the offspring after mutation, this number that is out of the range of this decision variable? Okay, so this just explains what to do. If bound, exit, discard, and generate again. Yeah. So to look at this closely, that means we are going to add a random number into this element. Yeah. Okay, now take a look at this example. Mutation weight, that is 20%. Yeah, so that means 20% of the population we are going to perform mutation. According to the equation right here in this bit, mu, this is mute, this 7, that is coming up from 8 minus 1, because in this example the n pop, that is 8, and then we are not going, we implement elitism, so this one we are not going to do mutation. So 8 minus 1, that means we will only perform mutation for the lower 7 times 2, because we have n y, that is 2. We only have x, y, 2 decision variable. So 2.8, roughly, we are going to round it to the nearest integer. So we are going to randomly pick 3 variables in the lower 7 chromosomes to perform mutation. For example, one thing we can do, that is randomly generate the row numbers and column number. Now, say this 4, 1, it means that in the 4th row, 1, 2, 3, 4, this is the 4th row. The first column, that is this guy. This guy we are going to do right here using the equation, that is p and pi equals p and plus sigma plus n 0 1. So pn, that is 5.6130, and then this number, at the moment I do not provide the information, I just know that this is a random number. So after performing this equation, after calculating this equation, Pn prime at this position, that is 9.819. Yeah. So this is the second position, this is the third position, and so and so. So after mutation, this is the new population. We are going to evaluate the cost for each one of them, and then so rank the whole population and go to the next iteration.